Good morning everybody, welcome to Smart Materials and Intelligent System Design. In the Composite Materials 4, we had round on the classical laminated plate theory. We are now at the fifth and the final round of composite material. What we had studied in the last lecture, if you remember, we had talked about the classical laminated plate theory based on Kartsov-Slave assumptions, and then we also have talked about how to get the force and moment resultants. Okay. What was we also referred as stress resultants, right. So, there were normal forces, shear force as in the form of stress resultant. Then we also had, if you remember, that we had the mx, my and mxy, that is the 2 bending and 1 torsion. Okay. So, together these things were related in terms of ABD matrices. So, that we have to keep in our mind that these basic relationships always, that we had Nx, Ny, Nxy, which is called the N part of it, and Mx, My, Mxy, which is the M part, the bending part. So, and then we had this ABD matrix there. So, I said that we always divide it into 4 parts, right. A part, B part and D part. We also said what are the names of each one of them, right. If you remember that this is related to the stretching stiffness, this is related to the stretching bending coupling, this is the bending stiffness. So, here also the corresponding the deflections we will be putting, that is epsilon xy or gamma xy. People put it in both the ways, kappa x, kappa y and the twist, that is kappa xy. This was the relationship that we had developed in the last class. Now, what we are going to do today is that we are going to see that based on the changes in ABBDs, remember that is the plus point of having composites. And these changes, if you understand it well, you can actually develop very interesting smart composites also. So, we are going to see what are the changes in ABD matrix we can make and how does it reflect in terms of the behavior of the system. So, we are trying to go through the coupling of these ABD matrices, its application in CLPT, and also if there is a thermal or hygroscopic loading, how this system is going to behave. This is what will be our intention in this particular lecture. So, if we look at the ABD matrices, this time we have really split it into 2 parts. Okay. So, that means first of all we made this splitting, that let us look at each one of these, the normal shear stress part of it, the force part so to say, and the moment part separately. If you look at the force part of it, once again we have subdivided into 2 parts, one is the mid plane part and another is the curvature part. Now, if you look at the mid plane part first, this part, the A16, A26, what does it tell us? It tells us that in this case, if the matrix suppose becomes fully populated, then if I apply the normal forces, we will be able to generate shear strain by using the normal force, because of this coupling that is happening to the system, and vice versa. If I apply the shear force, we will be able to generate strains in the normal direction. So, that is why these A16, A26 are commonly referred as shear extension coupling. Now, going by the same way, here you are going to have the bending extension coupling. Okay. Why is it bending extension? Because in this part, as you can see, that if you have a bending here, this bending is going to affect the curvature in the x direction. Similarly, my in the y direction or mxy, the twist in the kappa xy direction. So, that is what is my bending extension coupling. And interestingly, from the force is also we have similar coupling, that means the normal force can generate not only the mid plane strains, which is fine, but can also generate curvature. Okay. Nx can generate kappa x, ny can generate kappa y and kappa xy. In fact, each one of them can generate each one of these things, because there is a fully populated one. And here in this part of the coupling, we also have the D16 D26 terms, which gives us the bending twisting coupling. So, what it means is that if I give a bending moment here, I am going to get a twisting strain because of the presence of the D16 terms. Okay. Similarly, My is going to give me this twisting, and on the other side also, if I apply Mxy, that is the torsion, I am going to get kappa x because of the torsion, okay, and kappa y because of the torsion. So, I am going to get this coupling from both the directions. So, this is what is my bending twisting coupling. So, in a nutshell, what this is telling us is that if ABD matrix is fully populated, all the stress resultants and the moment resultants and their corresponding extensions and the curvatures, they get fully coupled with each other. So, I can generate any one of these deformations in a plate by using any one of these terms. That is a great advantage that we exploit when we make actually smart laminated composite. So, these couplings, let us just check it once again. The extension shear coupling is due to A16 and A26 term, which is actually developing the in plane induced forces. So, you can see that that is what is Fx lambda Fy lambda, which cause shear deformation gamma xy 0. Normally, Fxy lambda is 0, but if it exists, then these things will be produced. Okay. And this can be produced by actually having a smart material layer. You can have the extension shear coupling, or by having suitable material property, you can have this coupling. Bending torsion coupling, that is happening because of D16 and D26 terms, and this will be inducing moments in both the Mx My, and that will create twisting. So, bending will create torsion and twisting, and similarly torsion will create bending deformation. And then the extension torsion coupling. So, here it is happening because of the B matrix B16 and B26. So, they will induce forces, and that will in turn create twisting in the system. Similarly, extension bending coupling due to B11 and B12, they will induce these forces, and that forces which is extensional force, that is going to create bending kappa x and kappa y. And what is the role of A12? Due to A12, you are going to get the extension coupling in the normal manner. And what is the role of D12? For example, you are going to get bending coupling. For example, the induced bending moment Mx lambda will cause the bending deformation curvature in the y direction kappa y, and similarly My lambda will create a curvature kappa x. Okay. So, A12 gives us the induced force, will give the force from x will create deformation in y, or force from y will create the deformation in x, and similarly D12 coupling will give moment from M creating deformation curvature in the y direction, and moment from y creating curvature in the x direction. So, this is the entire coupling thing, and each one of the term they gets which one is the term which is responsible for what we have to keep in our mind. So, there is some of this coupling effect, as you can see. Try to identify that which one is creating what. For example, can you see that the Nx here is the in plane stretching, but it is also creating moment here, the bending deformation here. So, there is a stretching bending coupling that is happening. So, which term gives us the stretching bending coupling? Let us go through the terms here, and you can see here that the extension bending coupling comes from B11 and B12. So, that means this particular system must be having non-zero B11 B12 terms. Here we are finding that there is a thermal effect, and that is also producing the bending. There is also thermal effects are generally treated as the similar just like the in plane stresses in the system. So, here also you have a bending stretching coupling. Here it is very interesting, you have you are applying the stretching, but you are getting something which is twisting actually. So, you can see that there is a twisting that is happening in this system. So, this is a twisting and stretching coupling. So, if I go back again, so which is giving me the coupling between extension and torsion, well, due to B16 and B26 we can have it. So, this could be one of the reasons why we are having it if B16 B26 are 0. If we look at the last example, what is happening here is that we are giving this extensional stress here, but we are going we are finding that there is a shear that is happening here. So, why is this happening? It is happening because of the extension shear coupling that is present in the system, and which is due to the term A16 and A26. So, if you have non-zero A16 and A26, you are going to get this extension and shear coupling in this system. So, that is thus we are having various systems in which, so this is for example, extension bending coupling. So, you can go through such deformation cases, please practice it, that if I give you a deformation case, you have to figure out that what kind of coupling is present in such a system. There is a beautiful application of this concept. The conventional aircraft, the metallic wings of this aircraft, for example, is you can see the wing here for of course, a fighter aircraft, and you can see that the wing actually bends and twists at this point, due to the aerodynamic loads. Now, how can we make a situation that it will bend, but it will not twist? Well, if you have a bending twisting coupling, that we have earlier told that you can have bending twisting coupling. So, you have for example, the bending torsion coupling due to D16 D26 terms. So, if you develop a composite wing having non-zero D16 D26 terms, you can actually generate a torsional counter force, so that it will only bend, but it will not twist, and that way the aircraft will have a better stability. So, these are some of the concepts that you can actually apply directly from the composite to modify the behavior of a system. Now, there are some special cases we will discuss. The first special case is that what if I have a single isotropic layer, isotropic, which means the properties will be same in all the directions. Well, in that case you will get first of all a decoupling, because as you know that the stretching will not affect the bending anymore, and not only that, the normal forces, as you can see, has no effect on the shear strain, shear deformation, and vice versa. And similarly, here you would see that the moments will not have any effect on the twisting. So, these terms are 0. So, for single isotropic layer, all these couplings you will be missing. That is why we would not go for a single isotropic layer, because we want to create most of the times all these things. How about if I go for a single spatially orthotropic laminate? In that case also, as you can see that these parts will be 0, and also these particular parts will be 0 in this particular case. You can in fact actually calculate it, that what will be A11, A12, etc. It is a good exercise, because it also verifies that how you are developing the ABD matrix, and quickly whether by giving such conditions, whether the ABD matrix is perfectly done or not. So, these are two very simple cases. Now, from there, if I go to slightly different case, in which the ply angles are such that with respect to the mid plane, if the next one is minus here, it is plus here, then the next one is plus here and minus here. This is what is called antisymmetric laminate. For the antisymmetric laminate, if you carry out the same exercise, what you are going to see is that there is no connectivity between the in plane stretching and shear. So, it is the stretching shear connectivity which is absent there, but B matrix is present there. So, that means you are going to have stretching bending coupling, and once again these parts will be 0. So, which means there is no connectivity between the bending and the twist or torsion. So, antisymmetric laminate we are having two things which is not possible. One is that normal stretching decoupled from shear. So, this is absent, and what is absent? That is the torsion decoupled from bending. So, an antisymmetric sequence will give us the special case, everything else will be present in the system. If we go to antisymmetric crossply, so that means you have this plus minus theta, but also you have these crossply sequences which is generally 0, 90 consists of these things of plus minus 45s etc. So, if you go to this kind of crossply sequences, you will see that not only your these this part 0 just like it was in the earlier case, but also B matrix most of the terms will be 0 as you can see here. Okay. So, that means there are many B matrix terms which gives us the stretching bending coupling kind of things. There are many such terms which will be 0 in it. Okay. So, that is a special case of antisymmetric laminate itself. Next is if I go to antisymmetric angle plies. For antisymmetric angle plies, which is once again of plus minus theta consists of that, you would see that these parts are 0 as usual. Okay. So, these couplings are not there, the stretching and shear coupling and the bending and twisting coupling, but also a good part of B matrix are 0 actually. Okay. So, for example, this part is 0. So, what it would mean is that even if I apply say for example, the normal force along the x direction, what it is going to affect is that I am going to get affected in epsilon x 0, epsilon y 0, but not in the shear, suppose corresponding to this condition, and also I am not going to generate kappa x, I am not going to generate kappa y, but only kappa x y because of this. So, this kind of things peculiarities you can find in the special case of antisymmetric angle ply system. Now, we have another very special case system which is known as quasi isotropic laminate. Okay, why is it called quasi isotropic? It is because it behaves almost like a isotropic laminate in the planar direction, but not out of plane direction. That is why it is not fully isotropic, but pseudo or quasi isotropic laminate. Now, you need very special angle conditions for it. If the ply angles are of this type plus 60 0 minus 60, okay, that is of pi by 3, or of this type minus 45 0 plus 45 90, that is of pi by 4. Okay. So, for 3 layers this is the sequence, and these are 3 layer system. For 4 layer system this should be the sequence. Okay. So, for some very specific such layer conditions, what you are going to see is that first of all A11 equals to A22. Well, that is what isotropy is telling us. A12 is nu A11 and A66 is 1 minus nu by 2 over A11. So, this is what is the quasi isotropy that is coming into the system. Also A16 and A26 equals to 0. So, this you can develop only if you develop this type of a particular angle conditions in terms of your design of the ply, then only it will behave like this, that in plane it will behave like an isotropic material. There is another very special case which is known as the balanced laminate. In the balanced laminate, it should be all equal thickness laminae of either 0, 90 or plus minus theta pair has to be there. So, in the ply angles you should be having either 0 degree plies or 90 degree plies, or you should be having plus and minus theta. So, in this case what you will see is that B matrix is 0. So, B matrix 0 means stretching bending coupling, stretching bending coupling is absent. Okay. Coupling is absent. Coupling is absent, and A16 and A26 equals to 0. So, what it means is that the normal stress and the shear strain coupling, that is also 0. Okay. Coupling is absent. This is a very special case where if the plies consists of all of equal angles of equal thickness and angles of either from 0 or from 90 or from plus minus theta, then we get this kind of a balanced condition of a laminate. Okay, so, now we come to the summary of all these laminated plate stiffness matrices. So, if we consider first of all what I have said, that the isotropic system, then what will be the Q matrix that would look like? The Q matrix will have all these 0 terms there, as you can see the Q bar for isotropic system, Q 1 bar and Q 2 bars. And what the A matrix, if I look at it, you can see that the A matrix has these coupling terms which are 0, okay. A16, A26 are 0, the B matrix is totally 0, and the D matrix also has these 0 terms in it. Okay. So, that is the isotropic case. Now, we would not be much using an isotropic case, we will come to spatially orthotropic case, which is like along the layer we have the conditions of Q matrix of this type, that these particular things are 0. Okay. So, the elastic constants they are not affected along the normal and the shear directions. So, with that kind of conditions, if I consider only a symmetric laminate, okay, what is a symmetric laminate? You remember that for a symmetric laminate you should have an angle condition such that with respect to the mid plane, suppose I am having 3 layers. So, if this is plus theta 1, then this also should be plus theta 1. If this is minus theta 2, then this also should be minus theta 2, and if this is plus theta 3, then the last layer here also is plus theta 3. So, this kind of conditions if you have, then you are first of all going to get these parts as 0, just like the isotropic case. So, very much similar to the isotropic case, B is 0, okay, and you are going to have these parts also as 0. So, in many sense, in a specially orthotropic symmetric laminate, it behaves very closely to an isotropic laminated system. But if I go to a cross-ply laminated system, cross-ply laminated systems I already told you could be something like 090. Okay. So, symmetric or 090, in this case it will not be symmetric, actually it will be something like 090 type of ply system. So, if it is a cross ply system like this, because symmetric anyway it will be 0, the B matrix. If it is a cross ply system like this, then you would see that the B matrix is not fully 0. There are some terms in the B matrix which are present, and however, in the D matrix it will behave just like it was in that symmetric case. But because of that non-zero B matrix, what you are going to have in this case is that you are going to have the stretching and bending coupling. So, this will give us the first time in considering all the other cases so far, the stretching bending coupling you will get in this particular case. Now, we come to generally orthotropic case. So, there is symmetric and antisymmetric of them. So, if I consider symmetric generally orthotropic case, then you can see that the Q matrix is fully populated, and you can see that A matrix is fully populated. There are no 0 terms there. D matrix is fully populated, but just because it is symmetric, then this part will be 0. So, there is no stretching, bending, coupling here, just like the other case. If however, I go for generally orthotropic antisymmetric, then we are going to see that once again the stretching, bending, coupling is back here, although some terms are 0, but it is back there, and because of antisymmetry once again we are losing this coupling between normal and shear strains coupling, normal stress shear strain or shear stress normal strain coupling, we will be losing that. Also the moment we lose that, we will be also losing bending and torsion coupling, those terms will be 0. So, this gives us a summary of the various laminated plate stiffness matrix. Now, we can also look at the ABD matrix from another point of view, that is earlier I told you that N M, what was the earlier relationship if you remember, was A B B D epsilon 0 kappa. Now, what if I am interested to know that the forces are known to me? Many cases it will be like that. That is why the stress resultants will be known to me, and I am interested to find out what is the deformation or what is the curvature, etc. Then it will be an inverse of the ABD matrix. Okay? And remember that ABD matrix, there is no guarantee that it will be a symmetric one. So, its inverse can be actually it is not equals to inverse of each one of them, it is not equals to that, okay, unless B equals to 0. So, we need to actually find out that what it will be. If B equals to 0, then of course, this becomes A inverse and D inverse. We need to find out otherwise the inverse, and we need to find out the new A bar, B bar, C bar, D bar matrix, etc. Sometimes we will have a mixed condition, that means we will be given the stresses in the that is applying normal stress, shear stress, etc., and the curvature, and we have to find out what is the normal strain, shear strain, etc., and the moment that is coming into the system. So, in that case the ABD matrix that we know will be modified to a new ABD matrix as has been shown here. These are actually generally useful inversions which you can keep with you for ready requirements. Now, one last case is that what if there is a thermal or a hygroscopic loading? Okay, how can this happen? Well, as you know that a composite laminate, once we make it, we also place it in what we call autoclave machines, right. That is the first source where this can happen, because in the autoclave we apply high temperature and pressure for curing. So, during this process, okay, we are applying the temperature. So, there will be a thermal expansion in the system. Now, every layer itself is an isotropic first of all, and secondly the layer to layer also, because of the change in the ply layer angle, there will be this stress that will be developing may vary. And similarly, once you have this composite coming off, then if it is subjected to moisture, composites are more prone in terms of absorption of moistures. Okay. So, in that case the absorption will happen, and once again it is directionally dependent and it is layer angle dependent. So, that is why we have one thermal coefficient along one, another along two direction, and similarly a moisture coefficient absorption along one direction, another along two direction. Okay. So, that means for x y also we have alpha x beta x and alpha y beta y. Now, alpha 1 and beta 1s etc., they can be found out by these simple relationships, provided I know what is the fiber and the matrix volume fraction, and I know the thermal expansion coefficients of each one of them. I can find out alpha 1, and similarly I can find out beta 1. Okay. So, through experiments people can determine these things. Similarly, alpha 2 can be found out by this expression and beta 2 can be found out by this expression. Now, once I know suppose alpha 1, beta 1, alpha 2, beta 2s, then we go to how do we integrate it in our system. Now, we have this thermal and hygroscopic loading. In this case, we have the effect of it in terms of the strain. We can very easily write it in once we know these coefficients, and then once I know the strains in Ex, Ey and Exy, we can very easily integrate that as additional terms. We have earlier talked about these two terms as additional terms in the strain, and then the stress strain relationship is developed. So, this can be done for thermal as well as for the hygroscopic. So, if I do that, we can actually represent these additional terms in the form of additional loading, as you have seen that H or T, each one of them is giving additional loading in shear or additional loading in moment, where the additional loading in shear or normal stress or additional loading in moment, they are defined by this relationship. So, this is a simple extension which will be useful in shape memory composites and also in other simple composite systems, but for a smart composite like shape memory it will be also useful. These are the references that you can use for your further study in this course. So, this is where I will put an end. In the next lecture, we will learn about modeling of smart materials. Thank you.